Francisco. In a quarter mile, use the left lane to turn left onto Junipero Serra Boulevard. Slightly left onto the I-280 North ramp. In 1,000 feet, merge onto I-280 North.
Transistors. Billions of them. They are the ones and zeros of our computer. The chip works by whizzing electrons from transistor to transistor. And the smaller you can make those transistors, the less the signals have to travel, so the faster they can compute. Plus, you can fit more transistors into the same area, resulting in a much more powerful chip. So for over 50 years, transistors got smaller and smaller. The number you could fit on a chip every 2 years. This became known as Moore's Law, named for Intel's co-founder Gordon Moore after he noticed the pattern back in 1965, and it's been one of the main drivers of the tech industry. But around 2015, progress came to a screeching halt, and we might have never gotten past it if it wasn't for a single company that makes these machines, the machines that saved Moore's Law.
Holy. This is a video about the most complicated commercial product humanity's ever built. That's insane. It costs a whopping $400 million, and it is so bizarre that I want to introduce it to you with a thought experiment. Imagine you are shrunk down to the size of an ant. And you're given a laser that's strong enough to melt through metal like butter. Next, a tiny droplet of molten tin, roughly the size of a white blood cell, is shot out in front of you around 250 kilometers per hour. And your task is to hit this not once, not twice, but 3 times in a row in 20 microseconds with your little laser. Well, that is exactly what this machine does. It hits one tiny tin droplet 3 times in a row, heating each one up to over 220,000 Kelvin. That's roughly 40 times hotter than the surface of the sun. And it doesn't just hit one droplet. It hits 50,000 droplets every single second.
How often do you miss a laser shot?
We don't miss them.
What? You do 150,000 laser shots a second and you don't miss one.
Exactly. The same machine also contains mirrors that might just be the smoothest objects in the universe. If you scale one up to the size of the Earth, then the largest bump would be no bigger than a playing court. On top of that, it is able to overlay one layer of a chip perfectly on top of another and never be off by more than 5 atoms. And this is all happening while parts of the machine limp around at accelerations of over 20 Gs. For 30 years, almost everyone thought that actually building this machine was impossible. And yet, it exists. There is only
दिखाया है
one
शायद
part.
आपने पता नहीं याद नहीं मुझे
So
दिखा
what is this?
सकते हो
And what is this
हम
impossible?
वॉक करते हुए गए थे शायद
This video is sponsored by Print. More about them and the end.
अपार्टमेंट था ना
Now, just as a quick aside, the makers of this machine didn't actually sponsor.
ओ भाई
We just thought that the science and engineering here were so cool that we had to make a video about it. So let's jump straight in.
To make a microchip, you start by taking silicon dioxide, usually from sand, and purifying it into ultra-pure, nearly 100% silicon chunks, which is then melted down in a special furnace. Next, you lower a small seed crystal into the vat. Silicon atoms attach to the crystal, extending its structure. Then you slowly raise the seed crystal while rotating it, and this results in a large single crystal silicon ingot.
This is where the seed crystal would be, and then you pull it out.
Can I touch it?
Yeah, you can.
It seems like you would not be able to hold this from here.
Yes.
It even feels fragile. Like if you, yeah, I'm scared to break it.
Yes.
It's easy more force.
The ingot is then cut into wafers with diamond wire saws, up to 5,000 of them, after which each wafer is carefully polished. Next, it's coated with a light-sensitive material called photoresist. There are different kinds, but in a positive photoresist, the areas exposed to light become weaker and more soluble. So if you shine light through a patterned mask, you can selectively weaken parts of that coating. Then you rinse the wafer with a basic solution to wash away the exposed photoresist, leaving the design imprinted. So now you can actually turn this pattern into physical structures. This is often done by etching into the uncovered silicon by using either
यहाँ से
pupils
तो
or
ट्रेन
plasma.
जाती होगी
And then you
ये वही
deposit
वाला
metal
ट्रेन का
like
लाइन
copper
नहीं
to
है
fill in those etched
ये इनका
lines.
ट्रैम वाला लाइन
As a last step, you wash away the remaining photoresist, and now you've made a single layer of the chip. We've simplified this cycle down to the main steps: coat, expose, etch, and deposit. It repeats for every single chip layer, and depending on the chip, there could be anywhere from 10 to 100 layers. The bottom layer is the transistors. This is the most complicated layer, requiring hundreds of steps that all need to be perfect. The higher layers are a little easier. These are the metal wires that carry signals and power. By the end, the completed wafer can have hundreds of chips, which are then cut into separate pieces, packaged, and put into products. But by far the hardest and most crucial step in the process is where you shine light through the mask and onto the wafer. This is photolithography. And that's because this step determines how small you can make the features.
At first, it seems simple. Light passes through the openings and it gets blocked by all the rest. But as you try to print smaller and smaller features, the gaps in the mask start to approach the wavelength of the light. And that causes problems.
And we can actually show it because I happen to have this is a mask, this is a reticle.
A reticle, or a mask, carries the design of one chip layer. This reticle is filled with microscopic lines and gaps around 670 nanometers across.
And if I take like a laser pointer, so this is a red laser,
Yep.
if I shine it through it, then you see this here.
The laser has a wavelength of around 650 nanometers. When light hits the reticle, its wavefronts bend as they pass through each gap. So each gap sends out waves that spread out and overlap. Now, let's just look at the light from these two gaps. When the peaks of one wave line up with the troughs of the other, we say that the two waves are out of phase and they cancel each other out, so you get dark spots. And when the peaks line up with the peaks, the two waves are in phase. They add up and you get bright spots.
You get interference, right? And you get a diffraction pattern.
Now, diffraction is inevitable. So instead of fighting it, designers actually use it to get the patterns they want. They kind of work backwards from the eventual pattern they want on the wafer, and they design the slits so that diffraction will occur in such a way that it creates the pattern that they want.
You see three dots. The middle dot, that's the original one, that's the zero order. And then on the left and the right, you can see the first and the minus first. Now, in order for us to have this image resolved on the wafer, you need to capture the zero and the first and the minus first order.
The smaller you make the features, the larger this angle alpha between the zero and first orders becomes. So the larger your lens needs to be to capture the light. The size of the lens is described by the numerical aperture, or NA for short, which is just the sign of this angle. So the larger that is, the smaller the features you can print. But there is a hard limit to how large your lens system can be. When this angle is 90 degrees and your numerical aperture is 1, well, your lens would have to be infinite. Fortunately, there is one other thing we can change.
This is a red laser.
Yeah.
And a red laser has a wavelength of 650 nanometers, I would say.
Yep.
And if I take
Are to match up in phase again. So the orders end up closer together. So with a smaller wavelength, you can print smaller patterns using the same lens. All of this is captured by the Rayleigh equation, which determines the smallest feature size or critical dimension.
But since there's a limit to how much you can increase the numerical aperture, to 1, over time the only way to keep making smaller and smaller features is by using shorter and shorter wavelengths. So this is exactly what happened up until the late 1990s, when the industry settled on 193 nanometer deep UV light.
वो
This was the
कार की
light
हेडलाइट्स
used to
देखो
make
इसमें
all of the most advanced chips right until around 2050.
तुम्हारा कैमरे का
But by
शटर
that point, scientists had reached
speed
the limit
is
to how small they could
Ah.
make features. And Moore's law was about to run into a brick wall. So a radical change was needed. A change that had been brewing for around 30 years. All the way back in the 1980s, Japanese scientist Hiro Kinoshita came up with a crazy idea. Why not use most of their atoms? So most materials sort them. But unlike medical X-rays, which have wavelengths shorter than 1 nanometer, these are still long enough to